I'm Scott Constable. I am a kind of, I came into this at least as an outsider. This effort to bring in these new microarchitectural weakness definitions really started about 3 years ago, and I'll go through the timeline in the middle of this presentation. And at that time, I was very new to CWE. I hadn't heard of it. I was familiar already with CVE, but I didn't understand what CWE was, what its purpose was, and how it related to CVE. And as much as this has been a learning experience for me, I think it was probably a little bit different for me because I came to it so much later after CWE had already matured so much. And really interacting with the process through iterations of doing the submission, doing the presentations, and sort of building a working group, and then eventually moving the proposal to GitHub and working through feedback on GitHub, taking this whole thing through the process from start to finish. I'm going to present kind of my perspective on that and interweave it with some discussion on the nuances and subtleties of these new weakness descriptions that are very complex. I'm going to start with a recap of the transient execution weaknesses, the microarchitectural weaknesses that relate to transient execution before CWE version 4.14 was released. And I presented a couple different versions of this in the past. I've got a different example this time, so I hope I'll keep it kind of fresh and interesting for everyone in the audience. Then I've got a timeline showing step by step how we took this proposal through from just an original kind of kernel of an idea, working with MITRE, working with the other CWE community contributors to really mature and refine the proposal and incorporate feedback and discussion, how long that took, and the steps in the process and what our experience was like. Then I will present an overview of the new weaknesses with a motivating example. And finally, I'll point that Bob wanted me to really stress is to kind of clarify the nuances and the differences between each of the four new CWE entries. And please, I didn't make this deck with the intent that it would take a full 40 minutes of just me presenting. So if there are any questions at any point, please feel free to interrupt. You won't derail anything. You won't cause me to run over the allotted time, I guarantee. All right, here's my first example. This was a CVE that Intel issued in 2021. The description of the vulnerability is, quote, observable response discrepancy in some Intel processors may allow an authorized user to potentially enable information disclosure via local access. Um, it's okay, but it, at least for me, it doesn't give me much information about what the vulnerability is, what the root cause is, what the impact might be. It is a transient execution vulnerability, I can tell you that, but that's just from my own knowledge. This description doesn't say that. So why do we have this description? Well, if you dig further in this Intel Security Advisory, you can find a link to another technical document, and then this technical document elaborates where the CVE does not. And the technical advisory says that this is an in-domain transient execution methodology known as speculative code store bypass that may allow data values to be inferred during the transient execution of self-modifying code on some Intel processors. Now, big question is, why do we need to describe what the vulnerability actually is in a separate document, not in the CVE itself? Why doesn't the CVE itself just describe the issue so that we can understand, right? In a single sentence, you get an idea of what it is in the second description in the technical advisory, but why not in the security advisory with the CVE? Well, what I learned in my brief and quick introduction to CWE back in 2021 is that when we issue CVEs, we're supposed to adopt or draw language from an existing CWE description. And there's a fairly large corpus now of CWE descriptions. There are many for software. There are fewer, but a growing number of them for hardware. And the convention for assigning CVEs is to adopt the CWE language for the most specific CWE that describes the issue. And in this case, for this vulnerability, we thought that CWE 204 was actually the most specific CWE that describes this vulnerability. And CWE 204, of course, is not a specific CWE. It is a more, in the hierarchy of CWEs, it's more abstract. It's kind of, I think it's a direct child of 203, if I'm not mistaken, but it's sort of describing a side channel type behavior where the product, whatever it is, responds differently depending on the incoming requests or the state of the product. It's very abstract, and it's sort of hard to adapt this language and this description to any particular issue. But following the CWE conventions, this was actually the closest thing that we found for speculative code store bypass that was still accurate to describe the issue. Before this issue, there are some other CWEs that are more specific, but not accurate in describing this particular issue, speculative code store bypass. So it's I think a few times in the past, Intel had used some of these descriptions when they were applicable. But for this one, they weren't. There was nothing specific that applies to speculative code store bypass. And I'll talk through the reasons why now. So first, CWE 1037, the developer builds a security critical protection mechanism into the software, but the processor optimizes the execution of the program such that the mechanism is removed or modified. Okay, why doesn't this apply? So first, I'll elaborate a little bit more on speculative code store bypass. If you can think of like a just-in-time compiler or some of these managed languages like, say, Python, that they generate assembly code just in time. As they're executing these very high-level functions, they're constantly generating new code. That's in contrast to a traditional statically compiled language like C or C++, where you generate all the code at compile time, and then you just have this fixed binary that you can put in execute-only non-writable memory. That's not how JITs work. JITs like that run JavaScript or Python are constantly generating new code and sometimes overwriting old code. And what the processor does as it's executing code is it has lots of different places where it caches code. It has instruction caches, micro-op caches, and as it's executing code, it operates on the assumption that usually the code is not going to change. But if it does change, the processor might have already executed some stale code that had been overwritten in the intervening time. And when it does that, it might contribute to the introduction of vulnerabilities. And that vulnerability is called speculative code store bypass. So this doesn't circumvent specific security critical protections built into the JIT. It's not as though the developer intends or even understands that when one sequence of code is overwritten with another one, the processor might still execute the stale code. It's not like there's a particular bounds check or security check that the developer is going to put in the software to try to manage that, and the hardware optimizes around it. So CWE 1037 was definitely not applicable to this speculative code store bypass. The next one, CWE 1264, reads, the hardware logic for error handling and security checks can incorrectly forward data before the security check is complete. The speculative, the self-modifying code machine clear, also known as an SMC nuke, is not an error handling check. It is not a security check. It is an out of order mechanism that is in place that detects when code has been modified after the code has potentially already been executed and unwinds the pipeline and then starts from the point where the modification happened and re-executes, reloads all that code. It's not error handling. It's not a security check. CWE 1303 reads that hardware resources shared across execution contexts, for example, caches and branch predictors, can violate the expected architecture isolation between contexts. Shared resources are not a necessary ingredient of an exploit that could be built on speculative code store bypass behavior. Like many other kinds of transient execution vulnerabilities, this could, at least in theory, be exploited over a network by sending packets to a remote server, and then that server is processing the packets. Maybe that's influencing the generation of JITted code, and then if that overwrites stale code in a certain way, you can get some leakage that could be detected in the latency of the packets returning to you. So that's too specific for the speculative code store bypass. And for that reason, 1303 is too specific for many of these vulnerabilities. Then there's 1342, whose title is actually, it's very apt, I think, but the description is not. The description reads, the processor does not properly clear microarchitectural state after incorrect microcode assists or speculative execution, resulting in transient execution. In a sense, you could argue that this is correct if the processor did, in fact, clear all of the microarchitectural state as soon as the code is overwritten. That would mitigate the issue, but that would also be incredibly impractical. You'd have to really build an in-order machine, like going back to the 1980s. We had machines that were like that, that would literally wait until every store is written back to memory and updated across all the cores. And so you know that the code you're about to execute cannot be stale. You'd end up with very, very slow processors if you had implemented all of them according to that principle. So this, it doesn't really reply. We'd be very reluctant to use this description because it sort of prescribes a particular mitigation that I think most commodity hardware vendors would be very reluctant to ever implement to mitigate one of these issues. Oh, okay. I also had animated all this. I forgot to click through those animations. Okay. Now I'll take us through. Okay, before I move to the second section, are there any questions on the first section and why these, why any of these existing CWEs were insufficient or impractical, and why we felt the need to do a new proposal? Any questions? Okay. So this started about, what was it now? 2.5 years ago. The same year that we issued a CVE for speculative code store bypass, Priya and I first discussed these challenges, and it was her explaining to me what CWE is, how Intel uses CWE. I was learning at that point for the first time, reading through the descriptions, trying to get a feel for what CWE is and how it relates to CVE. So after a few months, we developed a proposal, we reviewed it, and we submitted it to MITRE for one new hardware CWE that we could just sort of intended this as a sort of patch to fill the gaps that we saw in those existing 4 CWEs that could apply to microarchitectural or transient execution weaknesses. Then a few months later, in September of 2022, MITRE asked us to present at the CWE Hardware SIG. So I presented something like what I just presented now, looking at those 4 CWEs, walking through why they're insufficient. I think back then I used a different example. It was the original Spectre bounce check bypass vulnerability. And after that discussion, MITRE and the CWE community asked us to expand the proposal and maybe propose several new CWEs that could more accurately and representatively characterize these transient execution weaknesses. Then in October, the next month, we presented a new hierarchy of CWEs, and this was the first version that had 4 discrete CWEs. And we started taking a lot of the existing publicly disclosed vulnerabilities and putting them into buckets and seeing how we could build a kind of new hierarchy. And then there's just one parent-child relationship. We had one that was going to be a parent of data forwarding, and then we had a couple separate CWEs for dealing with predictor state. And we got some very good feedback from this group. I'm really glad we didn't go with that original proposal, with that original hierarchy. So then we came back, we did some revisions, and we provided our first draft documentation in December of 2022, and that had a slightly revised version of these 4 CWEs. And over the next 9 or 10 months, we worked with, so that we had an ongoing kind of series of discussions. This took place over email. Eventually, it moved to GitHub, and I think that was a really, really good experience. I think GitHub is a very good platform for having these kinds of discussions, especially once you get the documentation and you start building the full descriptions and adding examples, and you can have more people collaborate and contribute and also add comments and tag particular lines in the document. I think it worked really well for anyone who did contribute and work with the system on GitHub. And so that involved Intel, AMD, ARM, Riscure, and CWE, as well as several MITRE folks that gave us lots of feedback, and we're very grateful for that. I think that improved the proposals an awful lot, but that took several months. And then in October, the proposal outline, so that was title, description, and extended description was accepted. And then we got the task of the more arduous but very important task of filling out the remainder of the required fields. And that included describing best known methods for mitigation, detection methods, observed examples, demonstrative examples, references, modes of introduction. There's a lot to put together, but it was great. It was an educational experience for us at Intel, for myself to actually go out and collect all this information and put it all into one place. And the great thing is it's public and everyone can see it. It was really, really, I'm glad we signed up for this. I think it was very educational and informative for everyone involved, including especially myself. And then we arrive at February 2023 when the new CWEs were incorporated into CWE 4.14, and it happened on Leap Day, which is very special. Okay, that's the second topic. Any questions, comments, anything at this point? How am I doing on time? Yeah, I think I'm about halfway through. Okay.
You got time.
Great. All right, and so here we are with this new set of 4 CWEs, CWE 14, 20, 21, 22, and 23. And Bob mentioned the blog that Intel published. I think there's also a blog that CWE published, so I'd also recommend people check that out. Hopefully someone can put that link in the chat. There's also a very good summary of the whole effort and the outcomes. In Intel's blog, I put this table in there, and I did it with these underlines, and this was very, very intentional. As a CWE outsider, from my perspective, and the way Priya explained it to me at the beginning, is that these descriptions should serve as a kind of template. You don't just use the intent of the description, you really should use the language, or the description should be crafted in such a way where the language is adaptable to a variety of vulnerabilities, conceivably any vulnerability that would fall into that category. And that's what we tried to do with these descriptions, is to structure them in some way, in such a way that they can be treated as a template. So here I kind of underlined each of the phrases in each of the descriptions that could be substituted with a more specific phrase for each issue, or elaborated upon, or kept the same if it's fine as is. And I'm going to walk through that same example I started with, speculative code store bypass. So in this case, speculative code store bypass, it doesn't fall into any of 1421, 1422, or 1423. It can't leak architecturally restricted data. It's not that type of a vulnerability, so it's not 1421. It doesn't involve stale data forwarding, so it's not 1422. And it doesn't involve microarchitectural predictors or predictor state at all, so it doesn't fall into 1423. And by default, then, it goes into the CWE that is most specific, that still captures the issue, and that would be 1420 in this case. And I think 1420 is structured in a way that is very, very flexible. You can use this language to describe a wide variety of transient execution vulnerabilities without changing very much in the description. So I'll walk through that now for how we would do this for speculative code store bypass. And just a reminder, the original description, the best thing we could possibly come up with while adhering to the CWE CVE standards was observable response discrepancy in some Intel processors may allow an authorized user to potentially enable information disclosure via local access. Very vague. So for the new description, I'm just going to replace processor, event, or prediction with whatever the actual event is. And in this case, it's a machine clear triggered by self-modified code. Then may allow either incorrect operations or correct operations with incorrect data. In this case, it's incorrect operations because the instructions that are executed after the code has been modified, they would be stale operations, so incorrect operations, to execute transiently, potentially exposing data over a covert channel. I didn't feel the need to elaborate or be more specific on which data. There might be other cases where it is very specific data. There's, just as one example, there's another vulnerability, rogue system register read, where user mode can transiently read model-specific registers that are supposed to only be readable in ring 0 in kernel mode. And then you could just elaborate on data to say, data in kernel accessible machine registers or something like that. But in this case, data is not really specific. It's data somewhere within the program that could potentially leak. Maybe if you're talking about a browser and it is compartmentalizing different browser tabs or different web domains, maybe you could get data from a different web domain, but there's no need to be that specific in this case because it really depends on the software that is impacted. So just potentially exposing data over a covert channel. And that's it. And now I think that's much more readable. It highlights the root cause. It gives the reader a sense of what the impact is. And now you don't have to rely on going someplace else to actually understand what this CVE would be disclosing. Now, this is the part where I'm going to talk about nuances, because I think there is some nuance. And as we were finalizing the CWE descriptions, I kept getting the same sort of feedback that a few of these seem very close or seem like they are overlapping. And it might be sort of confusing whether, in some cases, to use CWE 1421 or CWE, what was the other one? 1422. There are some cases where sort of behaviors in both contribute to the same vulnerability, and how is that supposed to work? So I made this flow chart to illustrate it, and maybe this could sit somewhere for posterity. But I'm not sure it's entirely necessary, and I'll explain why in a minute. But this will take anyone who's issuing a CVE for a transient execution vulnerability and step by step get you to the correct CWE or the intended CWE for that vulnerability. So this flows from left to right. If the weakness can expose data during transient execution, well, if it can't look elsewhere, you're not going to find something useful in this hierarchy. And if it can expose data during transient execution, then we're going to start enumerating these CWEs and find the right one. So the first question is, can the weakness expose architecturally restricted data? And if it can, then it's definitely got to be CWE 2021. And there may be a lot of different ways that could happen. It might involve predictors. It might not. It might involve race conditions between security checks and data accesses. It might not. It might involve stale data. It might not. Regardless, if it exposes architecturally restricted data to a logical processor that's in a mode where it's not supposed to have any access to that data, regardless of what instructions it's executing, that should fall into CWE 1421. Now, if we've established that that's not a component of the vulnerability, then we move to the next box. I should use my cursor to highlight these. Does the weakness allow predictor training in one domain to influence behavior in another domain? So this is like the branch target injection, or the Spectre v2. That was one of the very first transient execution vulnerabilities that was disclosed in January of 2018, where you could have, say, one sibling hyperthread that's training branch predictors while the other sibling hyperthread is consuming those predictor entries. So you get this very indirect method of controlling another domain on the same CPU. That would fall into CWE 1423. Okay, if it's not that, if it's not predictor sharing that is the root cause, then we go to the next block. Is the weakness caused by stale or incorrect data forwarding? And there are several vulnerabilities where this plays a role. I think load value injection is one of the ones that maybe got more attention. And then that would fall into CWE 1422. And then if it is none of those more kinds of specific root causes or specific behaviors, then the behavior can be categorized under CWE 1420, which is a parent of the other three. Okay. I think this flowchart is useful. I see I'm missing there should be a no here. I missed that. But of course, this isn't going to go on it's not a part of the CWE schema. I don't think it's going to go onto those entries, but I also don't think it's necessary. And the reason why is the way we addressed this concern while we were drafting the full proposal is we added some CWE mapping notes. And I understand this is a relatively new feature of CWE. I think it's very, very useful for this sort of situation where you have these root causes, these weaknesses that are much more complex, that are often a kind of interplay between different behaviors, the composition of which can lead to a potential vulnerability. Then I think it's very helpful to have these vulnerability mapping notes. And I think the The one that I got the most questions about was how do we distinguish between 1422 and 1421, because there are a lot of vulnerabilities that involve elements of both. How do we choose? And so this is the vulnerability mapping notes in 1422. It has a comment here. It says, use only when the weakness arises from forwarding of stale or incorrect data, and the data is not architecturally restricted. If a weakness does arise from forwarding of incorrect or stale data that is not accessible within the current processor context, then CWE 1421 may be more appropriate for the mapping task. And I think that's very helpful. So CWE 1421, if it involves kind of both aspects, CWE 1421 gets precedence over CWE 1422. So I just cited load value injection as one example where the data that is forwarded during transient execution already belongs to the current process. It's already in the same address space. It's already accessible. So that's one of the cases where it would fall into CWE 1422. And then I think we added these mapping notes in some form to all of the other CWE entries. And I hope that that will resolve any questions that any community member has when using these CWE entries.
Excuse me, Scott.
Yeah.
There's a question from Jason Oberg.
Sure.
Hey Scott, no, this is great. I like this this flow chart a lot. One thing too, I think at least how I see this is that there is obviously some overlap between. I shouldn't say overlap, but I would say a lot of vulnerabilities are, I think, inclusive of more than one of these weaknesses. For example, like a shared microarchitecture resource is a common weakness, but you may have a forwarding issue in addition to that. Do you see this the same way, that basically a vulnerability could have multiple of these weaknesses?
Okay. Yes. Yeah, I think that the short answer is yes, and this is a discussion that we had several times when we were kind of structuring the hierarchy. So I could talk through an example. Okay, I'm getting an echo from you, Jason. If you
Oh,
could
sorry.
mute yourself
I'll
if
mute,
you're
yeah,
not
sorry.
talking. I talked about LVI, load value injection, and it is related to another family of vulnerabilities called microarchitectural data sampling, or MDS. And the salient difference between those two is with MDS, you can get data from another domain. So that might be architecturally restricted data. And with LVI, you're really getting your own data back. That's the salient difference. But what happens in the processor pipeline is actually it's the same sort of thing. It's stale data being forwarded after or during a microcode assist, in parallel with a microcode assist or a fault or some other processor event. So one of the reasons that we wanted to be very direct and careful that these should be in two separate categories is that they might have to be mitigated differently. So for example, one way that you could address the case of restricted data is clearing microarchitectural state when transitioning to another context. So I'm coming out of kernel mode. I clear the microarchitectural state and any buffers that might be stale that could get have data forwarded from them. And so I might mitigate the weakness that way. Whereas with load value injection, you might not have such a direct way to do that because it's your own stale data you're getting back. And if we had structured these vulnerabilities in such a way where those two would fall into the same category, then you might have one CVE, but then you can kind of mitigate one of the root causes one way and mitigate the other root cause a different way. And it seemed like it would make the task of communicating about vulnerabilities and their impacts and their mitigations much more challenging. I think it's easier to have separate categories for those two cases because they have different impacts and they might have drastically different mitigations and treatments. And through our collaborative discussion, we arrived on this way of doing it. And maybe for that reason, it is a little bit more confusing to read these descriptions and understand the differences. But fortunately, we have these mapping notes. But in practice, when actually issuing CVEs, issuing guidance, I think this makes life easier for both the hardware vendor and the customers who have to follow the guidance.
Yeah, no, Scott, I think that makes complete sense. I mean, I think what I was trying to get at was really that if I look at a new vulnerability being disclosed, there's obviously the proactive side of using CWEs to prevent them, but obviously if a new vulnerability is disclosed and we're thinking about mappings, it seems reasonable that the CNA could enter more than one of these weaknesses. I think in a perfect world they would select just one, but there may be components of more than one of these weaknesses.
Yeah, perfect
that was
is
a
the
punch
enemy of the
yeah.
good, right?
Yeah.
And
I mean, I think we
there
made a
was
huge
at one
progress
point-
because right now weaknesses or CWs aren't entered at all. So
Yeah. At one point, there was a hierarchy. Maybe it was the first proposal or the second proposal. I think there were a total of 5 or 6 versions, actually. I only showed 2 or 3, but there were really 5 or 6. And one of those, it really was that there was no overlap between them. They were completely discrete. And the discussion that came out, that we got feedback internally, I was surprised to get the same feedback when I presented before this forum, that having that very rigid structure would actually make the CWEs less usable, less adoptable. So then we moved into this categorization. Okay, I think that is. Oh yes. I already talked about this a little bit. This is the other content that's in these CWEs, and it took a lot of time to put all this together. Thank you so much to everyone in the CWE community. There were also some people internally at Intel who helped contribute some of these, and we ended up getting a lot of information into these CWEs. I know there are some of them that have been around for a while, and it looks like they've been revised several times, and they've become very, very comprehensive with the scope of the mitigations and detection methods and examples that they have. And I think these from the beginning, they seem to be very, very comprehensive. But of course, I think there's always room to add more, and we're always learning more about these. As vulnerabilities go, this is a very young category of weaknesses. It's only about 6 years old, so there will probably be more added to these in the future, and I look forward to that. That's everything I have. So I think there's still a few. I still have 1 minute left in my allotted time. That's great. If there are any questions. Okay. If not, thank you very much, everyone, for listening.